Good afternoon, ladies and gentlemen. Yeah, we finally arrived in Busan City now. Today, it's really honored to introduce Professor Suhan Kim. He works at the Department of Civil Engineering in Pukyong National University. I have known the Professor Kim when I was doctoral degree in GIST, Gwangju Institute of Science and Technology. So maybe almost 10 to 15 years already.
Yeah.
So
10 to 15 years.
He's really honorable person at that time. Also, he has a good activity. He's supposed to give a 1-hour lecture today to us, but we are a little bit behind schedule. So I don't know. Maybe less than an hour lecture will be fine to us. Today he will introduce the system configuration for the Seawater Reverse Osmosis. So let's give him a big hand. Yeah, please.
예, 감사합니다. 이게 켜져 있나요?
예.
네. Okay, thank you for nice introduction and welcome to Busan. I heard that you have suffered from the traffic to come here. I'm sorry for that. But that is Busan, big city. Okay, today I'd like to talk about some system configuration for seawater reverse osmosis system for desalination. Because after my lecture, you will see this desalination plant. So based on the reverse osmosis membrane. So I think it will be great if I show you some basic concept of membrane-based desalination system. So these are contents of my lecture today. So actually I'm supposed to give you lectures about, anyway, the contents of my lecture today is, first is overview of the configuration for seawater desalination based on the membrane. Then I'll show you some components of the system, starting from intake to the cleaning and chemicals. So let's start from the overview. Okay, let's see this cartoon. So before we are operating desalination system, we need to construct. So this figure shows some construction. Before construction, we need to measure the water quality of seawater, if it is accepted for desalination or not. So if seawater is very dirty, you should not select that seawater for the desalination plant. And then this figure shows intake of seawater for the plant. And the next step is, what can you see? Yes, filtration, that's great. So we call this as a pre-treatment. So because even if we are selecting good seawater for desalination, still the water has some dirt, particles, and some pollutant. So we need to remove that bigger pollutant by using some filtration, or sometimes we are using membrane, another membrane. And this figure shows reverse osmosis membrane, like squashing seawater. So by using this process, we can separate salt from seawater. So by that, we can make fresh water. That is desalination. And the next step we call post-treatment. So if we are using that fresh water as drinking water, we need to put some hardness by putting calcium or magnesium. So that kind of process is called post-treatment. And next step and final step is distribution. So before distribution, we need to put some chlorine for disinfection during the distribution system. Okay, got it? So this figure looks like more, how can I say, more realistic. So this step is intake, as you can see from here, pre-treatment, reverse osmosis membrane, post-treatment, and finally distribution. So I can say again, intake, pre-treatment, reverse osmosis, post-treatment, and concentrate disposal. So the concentrate is produced from this reverse osmosis system. So because seawater is moved to the reverse osmosis membrane, seawater is filtered and salt is rejected. The water contained a lot of concentration of salt is called concentrate or retentate. Maybe concentrate is more famous word for that, concentrate. So we need to dispose the concentrate to the sea. Okay. So that is called discharge. Okay. So this is an example of reverse osmosis system configuration. So when you use the well water for intake, this water is rather clean because well water means if there is a seawater source, they move to the well via soil. So there could be natural filtration. So the well water is rather clean than the surface water. Okay? So you don't need to heavy pre-treatment step for this kind of system. So this unit is called cartridge filter. So usually this is not regarded as pre-treatment step, just for kind of to protect the high pressure pump for reverse osmosis membrane. And then if we take surface seawater, direct intake, in that case there would be the seawater may have some particles which may harm the reverse osmosis membrane. So we need to remove them first. So this figure, these two units shows some media filter made of some sand, gravel, or anthracite, that kind of media. So we need this pre-treatment step for to intake this surface seawater. And for disinfection of seawater, we need to put chlorine in the seawater. In that case, this chlorine may harm on the reverse osmosis membrane. So we need to remove chlorine before it reaches to the reverse osmosis membrane. So we put this chemical, it is called sodium bisulfite, or shortly we call this as SBS, sodium bisulfite. This one, SBS, to remove chlorine, to protect the membrane. So this is just an example. You will listen to the details of this unit system again, later. So this is the same system. The only change is this one is changed into this one. So usually we draw this kind of figure for some media filter operated by pump, you know. And this system just the natural gravity filter, yeah. So in summary, we can say the RO system consists of the following basic components: feed water supply unit, intake, pre-treatment system, pumping unit, membrane, and instrumentation and control system, kind of measuring water quality and some flow rate, pressure, etc. And permeate treatment and storage unit, which is called post-treatment, as I said before, post-treatment here, and cleaning unit. So even if we are doing pre-treat the seawater very well, there is a chance where reverse osmosis membrane is polluted by some pollutant remained in the seawater. So we need to clean up the seawater regularly, like once every week, not once every month, or twice every year, like that. So if seawater is very clean, the cleaning period is very longer.
You mean the membrane?
Yeah, membrane. So you should clean the membrane regularly.
Every 2 weeks?
No. That's my mistake. But maybe once every month, or twice. So ideal case is once every year or twice every year. Yeah. So let's see the intake and discharge first. So first case is intake by the well. So as I showed you earlier, if you take the seawater from the well, the water quality is rather good. So you don't need to worry about the pre-treatment very well. So this is some example of the well intake. And surface intake, in the case of surface intake, you need to worry about the pre-treatment, because the surface seawater taken from the surface, like that. Please look at this one. So if you directly take this seawater, there is a lot of turbidity in the seawater. Means a lot of particles contained in the seawater. So you need to filter the particle by the media filter. So this is an example of surface intake.
Down.
Yeah, down there. So more dirtier than this way. So even if we are taking this water, it is not that clean compared to this water. Okay? So if you take the well water, the water is filtered by the soil. Yeah. And this system shows put chlorine to disinfect the seawater. So if there is some microbes in the seawater, they will grow in the system. Pre-treatment system, reverse osmosis membrane. That means they can pollute the system. So in order to prevent that kind of situation, we need to put chlorine to kill the microbes. And sometimes you may want to put this ferric chloride. This is used as a coagulant to make some plug of the particles bigger. So bigger particles can be easily filtered by the pre-treatment media filter. Okay? So this is in the intake step. And let's see some top view. Oh, this is desalination system. This is intake point. This is discharging point. You know, in discharging point, the concentrated water comes out from this point. That means the concentration of concentrate is higher than the seawater. So it cannot be so close, because if concentrate comes to the intake, that is a disaster, you know. So, but let's look at this figure, number 62.1, not that far. So this distance is enough to pour some kind of.
Starting point, what's the use?
Just to throw away the concentrate. Yeah. Yeah. Yeah.
How about the depth of the intake and the discharge point?
I'm not so sure, but maybe the discharging point should be deeper. But if it is the case, the depth should not be very different. So kind of this figure. This is intake system. This is discharge system. but it looks like this one looks like a little deeper, but I'm not so sure. But you know, what can I say? The dilution of the concentrate from the plant is very, how can I say, very fast. So, for example, in this figure, this is kind of the discharge system called diffuser. So this is distance from distance in meters. Just more than 10 meters. This side concentration is changed into very similar to the seawater. So that is the reason why 62.1 meter is very enough distance.
Excuse me.
Yeah.
Which is the deeper? Intake or push and out?
You mean which one is deeper?
Yeah.
But I'm not so. I think I can answer that question.
No, this is discharge. This is the intake. Yeah. Or this is intake or discharge?
Is the difference between
Intake is deeper.
I think the intake one is better because it's clean to get water.
Really? Okay. Okay, thank you. I didn't know that. You guys told me. Thank you. So you mean intake point is deeper than the discharge point? Okay, great. Thank you. Nice. I didn't know that. You told me. You're a teacher. I was a student. Thank you very much. So please, how can I say? Please discuss while I'm giving a lecture. But it's very nice. This is important.
Discharge may be up.
Mhm.
The intake must be down. That is more natural.
That is more natural. Okay. Thank you. And this is another example of intake and disposal. But this is kind of some interesting example. When you take the seawater is stored in the lagoon and then moved to the power plant. And it is used as cooling water. Yeah. So after used as cooling water, you know, the temperature of seawater is a little bit increased. That means you need to put less pressure to filter the seawater. Because if temperature is increased, the viscosity of seawater is decreased. That means the friction of seawater between the membrane is decreased. That is the reason why when temperature is high, you don't need to put much energy or pressure for the system. Yeah, right. So this is seawater desalination plant, and the concentration moved to this discharge of the cooling water. Then that means the concentration of concentrate or discharged seawater is not that high in this case. This is what I showed before, diffuser. And so next step is pretreatment. This list shows that the required water quality information to design the reverse osmosis system and the pretreatment system, like temperature, pH, turbidity, and this ionic concentration, calcium, magnesium, sodium, potassium, barium, strontium. So this is related to some scaling, like barium, strontium, bicarbonate, calcium, magnesium. So this is related to scale. Turbidity, SDI, color, suspended solid, TOC. This is closely related to pretreatment. So for example, if you have high turbidity, you need to put more media filter in series, or you may think about putting membrane-based pretreatment system like microfiltration or ultrafiltration. So if you know the water quality of seawater very well, you can design the system. Membrane, not only for reverse osmosis, but also for pretreatment. So when you design the membrane-based desalination, the variety occurs in the pre-treatment system. Reverse osmosis is a very, how can I say, very fixed design. So you cannot change the configuration very much because just one thing you can select is the company of membrane manufacturer. You don't need to change a lot of things when you design the membrane, when you take the seawater. But pre-treatment, it's a lot of variety. If water is very dirty, you put a lot of, you need to process to remove that pollutant. If water is very clean, you don't need to worry about the pre-treatment. So that means, I say, there should be a lot of variety when you design the pre-treatment system. So this is kind of art of the design for seawater desalination.
Excuse me,
Yeah,
do you
yeah.
have the comparison about that? How many calcium, magnesium, potassium,
The next slide.
Real value?
no, what I mean, the comparison.
Comparison.
How many percent magnesium, sodium,
Uh,
percentage barium, strontium?
in seawater, you mean?
Yeah, for this.
I don't have right now. 혹시 자료 있냐? Excuse me.
Yeah.
So
Because this is the pre, isn't it? The pre-treatment.
yeah,
So you mentioned that for the RO,
Mhm.
it has been standard, no
Yeah,
variation.
yeah,
The
right.
quality of the water is become from the pre-treatment.
Yeah,
The
right.
question is between these amount,
So
sulfate,
in seawater,
do you have the composition?
yeah, I have the composition, but I don't have in my lecture file right now. So, but the concentration of these ionic components are like very constant in the seawater. Maybe a little different between when you take the seawater in this Busan area or Middle East area, that might be a little different. But the actual concentration is looks like very constant. So
Maybe what we need is the recommended values for each component.
you mean
The recommended value.
Yeah.
recommend values? You mean value of concentration?
Yes. So
You mean for design or just for some information?
Just information.
Just information. 이 인터넷이 되는지 모르겠네. 안 됩니까? 그거
Because
I think it's in the
the
next
key is
slide.
here.
The next slide is showing the.
yeah, this is a different thing. Yeah,
Different.
yeah,
What I
different
mean
thing.
is, you go to the first, okay.
Yeah.
What he said is maybe you can give the standard concentration. How many percentage the calcium, the magnesium, sodium, potassium underdown. So we can get the good quality input for the RO.
Okay. So the actual concentration of these ionic components is not that important for the to know water quality is good or not. This figure is more close to it. So good quality for reverse osmosis. This one maybe you want to. So you need to look over turbidity, SDI, which is called silt density index, and suspended solid. So these are representing for some particulate matters in the seawater, particle. So usually you are using, people are using SDI.
What is SDI?
So it is called silt density index. This is silt density index. So this is for particulate matters concentration in the seawater. So if this index is bigger than 5, that means you should not use that seawater for the desalination using reverse osmosis membrane. 5 is very important figure. And these days, membrane manufacturers, I mean reverse osmosis membrane manufacturers suggest to 3 for standard. More than 3, that means bad water. Less than 3, good water. So this is most important things. And these days we are we are looking at the TOC as another important parameter, but there's no specific standard for the TOC concentration. This means organic matter concentration. So this organic matter cannot be filtered by the media filter in pretreatment step. So it can be directly moved to the reverse osmosis membrane. Or it can be a good food for microbe, organic matter. So microbe can, how can I say, grow a lot on the membrane surface. That means the membrane surface is covered by the microbes and its related matter. That means the performance should be very poor. So the to select very good pretreatment step, you need to focus on this SDI index, silt density index. So if you cannot decrease this number down to the 3 or 5, you should put more step for the pretreatment. Okay. So to decrease this number SDI, or to get to get cleaner seawater for reverse osmosis, you can do a lot of, you can select a lot of unit process like coagulation, media filtration, some flotation, and membrane-based filtration. So let's talk about the coagulation first. For coagulation, you can use alum. This is an aluminum-based coagulant. Ferric chloride. This is iron-based coagulant. So this shows some optimum pH range for each coagulant. And you put the coagulant, make some bigger plug of the particles for better filtration or better sedimentation. So coagulant dosing rate is selected based on the result of jar test, which can be shown like this figure. So by doing this jar test, you can get very optimum concentration of a coagulant, which is called dosing rate. Sometimes you may want to change the pH range to get better coagulation, but this kind of step is not suggested to change pH just for coagulation, because that kind of job is kind of very complex for operators. They do not like that kind of complex things. Okay, just want to know how much concentration do I should put for coagulation. The next step is in seawater desalination, the sedimentation is not usually used. After coagulation, the bigger plug moves to the filtration step, so-called media filtration. So these are some subcategories of media filtration, like gravity filters, pressure filters. So gravity filters, we draw this way. This is pressure media filters. So which I told you earlier, this filter is operated by the pump. Yeah. Okay. So this is a picture of gravity filter. So the media is anthracite and sand. So sometimes people call this kind of filter as a dual media filter. Two media, dual media. Okay. This is another picture of gravity filter, pressure filter, still dual media, anthracite, sand. And this is,
Backwashing was applied to.
I'm sorry?
Backwashing was it applied to in the?
Backwash should be done
How's
in
the
this.
frequent? I mean, how many?
You mean the frequency of backwash? Maybe once a day or once every other day. For water treatment plant, but actually I don't know about this sewerage.
Is it based on the differential pressure?
Yeah, right. So if there's the surface of this media is polluted, the pressure difference between this one and this one is bigger, higher. So that is standard which I should select the backwash or not. So it's there is no absolute period for backwash. It's up to the water quality.
It usually works automatically.
Usually, the backwash was operated automatically, but sometimes operator can do the manually. And the usual period, what he said is the same as I said earlier, once a day or once every other day.
Sir,
Okay.
can we modify the design of the media filter? Maybe we can use another material, like say for example, we have a coco pit filter bed.
What filter?
For the filtration.
For the
part,
filtration, okay.
Can we? Is it possible to modify the design? Say for example, use of different material aside from anthracite.
I think, yeah, I
other
think you can
materials, like
do
we
that.
have
Yeah.
the coco pit filter bed.
Coco pit filter.
Yeah.
What is that one? Coconut?
Coconut
Coconut filter.
Yeah. Then
What is the size of the coconut?
I think it
medium?
depends on the material that we are going.
Oh, really? So is it comparable to the sand or anthracite, like 1 millimeter in diameter? This is 1 millimeter. So is that small? I mean, coconut particle?
Yes, because I think we can also check on that.
Yeah.
The,
I think the size is very important, and how can I say the rigidness? I mean, hard.
pore size.
I don't know the coconut particle very well. So if the size is similar to this one, and then the shape should not be changed by some pressure. I mean, how can I say rigidness? yeah. So then you can change that one. But what is the reason? The coconut particle is cheaper than this anthracite or sand?
Maybe much more popular in
Your area. Okay.
coconut.
That means
Yeah.
cheaper. maybe price.
Yes,
Maybe the matter of price. Yeah. Okay.
We're also using that for filtering materials and other pollutants for
Okay.
wastewater.
So this pre-treatment system is very similar to the unit process for drinking water production system. So if you have experience to use that coconut in this media filter in other area, like drinking water treatment plant, you can use that system. You can introduce that system to the pre-treatment for seawater. So you said you already have experience. I mean, in your country already
No, but
used
that's for wastewater.
Wastewater treatment.
wastewater treatment. Wastewater treatment, not drink. But maybe even if that is for wastewater treatment, the basic mechanism is the same. So I think I think you can try. I think. Not I. we don't have a lot of coconut in Korea, so it is very difficult.
This is local wisdom.
Okay, local wisdom. Okay, I learned again. Thank you. Thank you, teachers. So this is another pre-treatment system other than the media filter. So raw water mix. So in this step you put some coagulant. Then flocculator. In this step you can make the particle bigger flux. Then you put some micro bubbles. That is which is attached to the flux. That means the volume is increased, but density is not that increased because of the bubbles. So the flux with bubbles with floating. So dirty part of water is moved to here, and the cleaner part is moved to here. But in this step, so this is called dissolved air flotation, DAF. And next step means filtration, DAF and F. So the cleaner part moved to this media filter. So in this Gijang plant, they have ball filter for this step. So kind of a second barrier. First is floating, second is filtering. So this system is may be better compared to just filtration. So it can be comparable to the sedimentation and filtration. So sedimentation is comparable to the flotation. Sedimentation, flotation. Okay. And next thing is membrane-based pretreatment. So if you want to make sure very high quality water for reverse osmosis system, you may want to use the membrane like microfiltration and ultrafiltration. So if we can say the pore size of media filter is like 10 micrometer or 100 micrometer, this membrane has pore size less than 0.1 micrometer, very small. That means you need to put very high pressure to get the filtered water. But since the pore size is very small, the water quality should be very, very excellent. So you can, when you design reverse osmosis membrane, you can put less membrane area, because if water quality is very good, you can design higher flux. If flux is higher, there is more chances of some surface pollution, or which we can call that kind of thing as fouling. You can avoid fouling when you decrease flux. But if the water feed water is very clean, it is okay if you put more water. Okay? So that is the advantage of a membrane-based system, but it is expensive. And it needs higher electricity compared to the media filter. So just think about the gravity filter. You don't need to worry about the electricity. Just for backwash, you need to put the electricity. Okay? But in membrane-based system, you should operate always pump. So that is the reason why there's a lot of options for design of pretreatment. And still, we are focusing on SDI as a water quality silt density index, which I told you earlier, and TOC. So in case of TOC, there's no way. So media filter cannot remove the TOC very well. This membrane system cannot remove TOC. Only coagulant can remove a very small part of TOC. So I suggest to you not to select seawater with high TOC. So if you want to remove that TOC, you put another system like activated carbon or ultraviolet system. Expensive. Okay? So you better select cleaner seawater, because we have a lot of seawater source. Okay? And this is a cartridge filter, which I called the last stop before the seawater moved to the reverse osmosis membrane. And actual pore size of this cartridge filter is about 5 microns or 10 microns. So people, or reverse osmosis system operator do not expect the cartridge filter very well. This is just for safety. Sometimes the pre-treatment work. Sometimes there may be some case the pre-treatment system work. I'm sorry, does not work very well. If that is the case, kind of emergency, the cartridge filter can work. So after seawater comes to this way and filtered, the filtered water comes to this way. This way, this water is moved to the high pressure pump for reverse osmosis system. And next step is hydraulic units. There are two important hydraulic units in the reverse osmosis system. First one is high pressure pump. Second is energy recovery device. So this is pump. Without pump, you cannot filter the water by a membrane. Okay. This is an example of positive displacement pump. This is centrifugal pump. This is a pump. This is membrane vessel, which I will tell you later. And now let's talk about the energy recovery device. Since the pressure needed for the seawater filtration is very high, usually more than 50 bars, very high pressure. So, and usual recovery rate for the seawater desalination is about 50%. That means if you take 100 of seawater, you can make 50 of fresh water and 50 of concentrate. So that means 50 of concentrate has high pressure, high flow rate, combined energy. So this energy recovery device can utilize that energy and help this pump or electricity. So this is a picture for the turbine type ERD. Maybe the brand is turbocharger. Same picture, same product, turbocharger. This looks like a turbocharger in the real system. And this is another type of ERD, isobaric. So this is a schematic picture of the pressure exchanger. Pressure exchanger means a brand name for the isobaric type of ERD. This one. So without using ERD, you should put this kind of energy for unit water production. But when you use the turbine type ERD, you can decrease down the energy 2.6. So almost 4 to 2.6. But usually these days we prefer to use in the isobaric type of ERD like PX. And in this plant, they are using DeWeer. So when you use isobaric pressure exchanger, which is a kind of isobaric type ERD, then you can use this energy, 2.14. That's better than this one. That is the reason why people prefer using isobaric type. PX, pressure exchanger, is usually called PX or DeWeer, DWEER, DeWeer. So you can see DeWeer in this plant. So still people doing some research to decrease the energy of reverse osmosis system. As you can see from this figure, the most part of energy consumption is occupied by reverse osmosis system, usually by pump. So you can decrease. This number is obtained when you use energy recovery device. So if you are not using energy recovery device, the number should be bigger, higher. So now let's move on to membrane. So there are two types of membrane modules in the reverse osmosis market. The one is spiral wound, and the other is hollow fiber. So hollow fiber type membrane is made by Toyobo, which is Japan membrane manufacturer. But the market share of hollow fiber membrane is very small compared to the spiral wound. So you may think the more than 90% of market share is covered by the spiral wound membrane. The spiral wound membrane looks like this one. And this is usual type of spiral wound membrane element, or you can say membrane module. So 1 meter in length, 8 inch, or 200 millimeter in diameter. In this plant, they are using the 16-inch membrane, like this one, much bigger. Okay, and this set SWC3 element. This is made by Hydronautics, the company name. So in this plant, they are using the membrane made by the Dorei Chemical Korea. The model name is CSM. 맞죠? 감사합니다. So in membrane system, you should know the concept of pressure vessels. So pressure vessels is kind of some case of the four membrane modules, which can resist very high pressure, almost up to 80 bars, 90 bars. Because as I told you earlier, the minimum required pressure for seawater desalination is around more than 50 bars. And in Korea, we have winters. That means temperature is very down. So in that case, we may need to put higher pressure than 70 bars. So the pressure resistance of pressure vessel is very important. And stages and passes. So I'll explain the concept of stage and pass later. Just here. This is two-stage system. In two-stage system means the concentrate of the first stage is moved to the second stage to increase the recovery rate. So usually the concentrate is discharged. So instead of discharge, you use that water for the feed water for the next step. That means you can get more volume of fresh water, product water. So which results in increased recovery rate. So this is an example of two-stage membrane configuration. So 32 means the first stage of the number of pressure vessels. So 8. 4, that means 32. And these two collect the concentrate. Concentrate is moved to here, and this 14. 8, 6. So 14, okay? And 7M means in one pressure vessel, 7 membrane elements are placed, okay? 1, 2, 3, 4. You cannot see 7. You should believe me. 7 in one pressure vessel. Thank you. And there's another concept, pass. So this kind of multi-pass system is used to increase the water quality. So as you can see from here, this is permeate. Permeate moves to the next step. That means filtered first, second. That means much better water quality. So this kind of system is used to remove boron, B. So in seawater, usually in seawater has usually 4 to 6 milligram per liter of boron. So that is, and in our country, in Korea, the drinking water standard for boron is about, exactly 1 milligram per liter. Yeah, 1. And WHO requirement, not standards, they suggest, WHO suggested 2.4. 맞죠? 맞을 거예요. Maybe. I'm not so sure. I'm 99.
What is the numeric milligram or meter?
Milligram per liter. ppm. The same. ppm, milligram per liter. So seawater has 4 to 6. 4 to 6. 6. I'm sorry. 4 to 6. And reverse osmosis usually are not good at filtering boron. So people trying to use this multi-pass system to remove boron. So so Doosan have some system to treat boron kind of this way and some different way. And this table shows some the performance of membrane when it is tested in the factory. So model-based test. So only one model is tested, and this is a field. So it looks like brackish water membrane, not seawater membrane, because it is tested is 1500 ppm. You know, seawater is
50,000,
Yeah.
55,000.
right. Very good. So you should the performance of ex-factory test, I mean one model test and the real field test is different, because recovery rate is not the same when you use the one module, and this is kind of 14 modules, 2 to 1 array. That means 2-stage system, and 2 vessels in the first stage and 1 vessel in second stage. And 7M means 7 membrane modules in 1 vessel. So actual number of membrane elements or modules are 21. Okay? So this is just number of elements in series. In series 14, but actual number is 21. Okay? And now let's see how to select good membrane elements. Usually membrane manufacturers provide us some spec sheet. So that has very good information to select a better membrane for us. But sometimes you should be very careful. When test conditions are different, the performance should be different. So you should compare. When you compare 2 spec sheets, you should focus on the test conditions. So for example, when you put higher pressure for the test, the salt rejection ability of membrane looks like higher when you put higher pressure. So if one company is tested, if a company tested their membrane with like 50 bars, and another company tested their membrane is 60 bars. If the membrane abilities are the same, if we assume that the membrane performance are the same, the test with the higher pressure, like 60 bar, shows better water quality. So you should not be fooled by that kind of conditions. So please read these four very carefully. And this is an example of membrane elements in pressure vessels. So this x-axis means the element position. So we have 7 membrane in series in the pressure vessel. And y-axis means the salinity in ppm. So when you see in this, when seawater flows in this way, the water is filtered. That means the more concentrated water moves to the next step. So that is the reason why the salinity is increased. Okay. So the salinity is increased in the next element of membrane. So the permeate flow rate, or we can say flux should be decreased, because higher concentration means high osmotic pressure between the water, feed water, and the product water. So that means the net pressure should be decreased in this 7th membrane and the 1st membrane. Okay, so you can see this kind of result. Okay, now almost done. Control system. So we have in reverse osmosis system, we have feed water, permeate water. This one is product, seawater, fresh water, concentrate. Okay, so you can measure at least 2 flow rates, 3 pressures, 3 water quality, conductivity. So conductivity represents some salinity, temperatures, pH. So there is some measuring instruments for these points. And this slide shows the objective of the control system. Please read it, because we only have 15 minutes to finish my lecture. And control loop. Okay, this figure shows two type of operation. First one is the constant permeate flow. So if temperature of seawater is changed, or seawater or reverse osmosis membrane is fouled, covered by the pollutants, you may get some different water production rate. So to control that kind of situation, or you can say, if you want to make the constant production rate, you can change the pressure. So if flow rate is decreased, you should put more pressure. Increased, less pressure. That is a constant permeate flow control. And this one is a more complex one, the constant recovery rate control law. So in this case, you should control concentrate flow rate and permeate flow rate together. So you should change the how can I say, pump pressure by controlling inverter, and you should put some control valve to control the recovery rate constantly. And these are some equipment safety parameters. So if this kind of situation occurs, maybe the system should stop. And this is authority levels for the control system. So level 1 to anyone, or level 5 to program developer. Authority levels. And data recording and process controls. So data recording is very important. When you record data, and when you can see some history of the plant, so you can check the plant is operated good or bad by looking at the data. So this is very important thing. So next step is, the last step is the cleaning. So as I told you earlier, even if we are doing very intensive pre-treatment step, or we can select very good seawater, there should be a big chance of membrane fouling. So we need to clean the membrane regularly. So this is some requirements of the cleaning unit, and this is a conceptual figures. So in here, the chemical is input to the cleaning tank and clean the membrane system, and this filter is used to collect some dirt from the membrane. And heater is also very important. So if you clean your membrane with water with the high temperature, you can get the better performance. If you are using cold water, you cannot clean the membrane very well. So the using heater is very important, or selecting summer season is also very important. So I do not suggest to you to clean your membrane in winter season. So now let's move on to chemical injection. This is for intake in the well water. So you cannot see, you just see the exit tank and scale inhibitor to control the scaling in the reverse osmosis system. But in case of surface, you put a lot of chemicals for pre-treatment. You know, surface intake is a pre-treatment step. And this looks very complex. So intake chlorine, exit and perichloride, exit and perichloride for the coagulation, and exit and scale inhibitor for the inhibition of scaling and the reverse osmosis. And this one is used to remove this chlorine, because this chlorine can break the reverse osmosis membrane. So for post-treatment, you should change the RO product, permeate, usually called product, RO product quality using chemicals. So the frequently used chemical is lime, calcium carbonate, caustic. Caustic means sodium hydroxide and sodium carbonate. So lime, calcium carbonate, caustic, sodium carbonate. So to increase the hardness of. So hardness can be measured by the concentration of calcium or magnesium. So calcium and magnesium is divalent ions, 2 plus, 2 plus, Ca2 plus, Mg2 plus. So divalent ion can be rejected by reverse osmosis membrane more easily. So the hardness of the fresh water produced from the reverse osmosis membrane is very low. That is not good for the drinking water. So you need to put calcium, magnesium. Usually calcium is better than magnesium. Magnesium, the taste of magnesium is still very, very bitter. So this figure shows some usage of these chemicals for the end result of putting these chemicals. Hardness increase, alkalinity increase, TDS increase. So this figure shows putting lime plus carbon dioxide and acid for the pH control, chlorine for disinfection for the water distribution system. So this is the end of the slide, and I think if I show you the better lecture, it needs more than 5 hours or 5 hours to 10 hours. I have some experience to teach foreign people to our country. So first I taught a country in the Africa. Not Uganda. Kenya is last year. At that time, I think Egypt. There is some water authority. So the water authority in the Egypt, they come to here. In K-Water, there is Korea Water Resources Corporation in Korea. They went to K-Water to get some seawater desalination lectures. As far as I remember, I gave them for 14 hours of lecture using this slide. So in that case, you can learn how to measure SDI, what is important water parameter. So when I saw this program, there's a lot of lectures. And I'm giving you this lecture in this desalination plant. So I think my lecture will help you to understand this plant very well. Anyway, thank you very much. 감사합니다.